Time to get started. This week we've got Dr. Pierre Cauchy and Dr. Ahsan Raza. Pierre is going to kick us off. Pierre, will you give us a very quick introduction to yourself?
Hello, everybody. I'm speaking from Canada at the moment, so it's the morning. I have recently been appointed as a professor of marine acoustics at Institut des Sciences de la Mer in Rimouski, Quebec. And I will be presenting my work, my PhD work that I was doing at the UEA the past 4 years.
Super, great. And Ahsan?
Thank you, Ben. Welcome, everybody, and thank you for coming for today's session. My name is Ahsan, and I am basically an employee of University of Bath. I'm working on a collaboration project with Seish in Devon. So I'm currently in Devon countryside at the moment and joining you guys from there. Yes, and I'm working on a signal processing project, which hopefully I will discuss today with you guys. Thank you.
Great. Okay. Thank you very much, both. Okay. Well, Pierre, would you like to kick us off? I'll stop sharing my screen, and you can share yours.
Here we are. Can you see that?
Perfect.
Okay, good. Well, good. Hello, everyone. So the work I will present is what I was doing as a PhD student at the University of East Anglia. I was funded by Nexus and CFAS, and my thesis title is Ocean of Sound, Ocean Gliders Observing the Oceanic Environment. So I was working with gliders, which are, let me try this thing, laser pointer. So these autonomous submarines that are quite routinely used now by physical oceanographers to measure hydrographic profiles. And I was adding hydrophones to these, so that's what's here, to record the ambient noise and do some underwater acoustics from these measurements. Just a quick heads up on what gliders are. So they are about 1.5 meters long submarines full of batteries and oceanographic sensors. They are buoyancy driven, so they don't have a propeller. They have a bladder here that I've tried to represent of a varying size that allows them to either sink down to 1,000 meters or come back to the surface later. And they use this quite long, slow, vertical movement to glide forward towards the target direction. So they are able to travel for several months, thousands of kilometers, making measurements. And they have very limited flow noise because they are slow. They don't have propulsion, so that makes them very adapted to passive acoustic monitoring. This is a spectrogram of the dive I've just shown up there. So you have the start of the dive, lots of batteries moving, pumping noise, surface noise. Then you have, for what is this, 200 minutes roughly of silent gliding. Then bit of pumping again once you're at the bottom to come back up, another 200 minutes of no noise, and then back to the noisy surface. So out of, I have here 420 minutes, and we have roughly more than 300 minutes of silent movements where we can actually record and analyze the ambient noise. So that's what I was doing, and I've been lucky enough to piggyback my sensor on many gliders in many places of the world's oceans. Now, you may be more familiar with what the underwater soundscape is. There are three main types of source sounds. You have the geophony, which I've represented here in green, physical processes making noise. There's anthropophony in red, which is us making noise, and the marine life also makes noise in blue. I've mainly worked on geophony and biophony to start with, and I'm now more shifting towards anthropic noise. So that was my first paper of the PhD. I was working on wind noise. So if you look at this, this is 4 or 5 weeks of recording in the Mediterranean Sea, and if you zoom on the highish frequency sound, so that's around 3 kilohertz here. This is not linearly, but directly dominated by wind noise. So more wind, more noise. And I've shown that even using glider that moves from like quite a long distance vertically, we can still correct this and measure the wind speed from the ambient noise. So that has been published, I don't know, here. That has been published in 2018. And the implications of this work are that it will improve air-sea interaction measurements, because the wind speed is directly collocated with the measurement of the hydrographic profile from the glider. And I'm also hoping to extend this this type of measurements to stronger wind speeds. So this one was went up to 20 meters per second wind speed, which was already new. And I'm hoping to use gliders that would be deployed in tropical storms. There are also a project at the UEA from another PhD student to work on rain noise in the monsoon regions. And later on, we could adapt this technique to listen to ice noise in polar regions. I've also worked on marine life, so I have a couple sounds here. This doesn't play. So I have here, so this is a sperm whale recorded in the Mediterranean Sea again. So I have, sperm whales are quite easy to analyze. They have this very regular pattern of clicks. When you have several sperm whales, you have several easily identifiable clicks of trains. And in the Mediterranean Sea, you have to do not mistake them from dolphins, but it's not hard. I have here, I think, dolphin noise to see how different it is. So it was a. So I didn't do this processing automatically, but it's very easy to do this by hand. I have another one here, still another dolphin noise. So the processing was done manually, just looking at the spectrograms, and you see these very regular patterns on the spectrograms. I have them here actually. So that was maybe a couple of weeks of work to analyze 5 months of data. Just on 1 minute files, I was detecting presence or absence of sperm whales, and also detecting, classifying whether there was only one whale or potentially several whales. And that allowed me to make a map of presence and absence of sperm whales in the Mediterranean Sea. So we are here in the Med. This is Corsica, France, and Spain. I had 5 glider deployments, 2 of them going from France to Corsica, 2 going in the middle of the Gulf of Lyon, and a 5th one going just across the shelf here in Sardinia. And I've been able, along all of these lines, to just detect presence of sperm whales and to draw a map. So that's my map of detections. Stars show groups of whales, and triangles show single whales. And this analysis covered mostly winter months, so from December to April in 2012, and this deployment was in June 2013, so a bit different because 1 year after, in summer. Now, this is a very different way to look at whales compared to the usual way. So this is the ACOBAMS survey initiative. That's how you, at the moment, you count the number of whales in the Mediterranean Sea. So it's very larger scale survey. It's done with faster systems, either boats or planes. And this way, this technique provides a snapshot over a short period of time where you know that you move faster than the whale. So if you see it here, it's here. If you see another one somewhere else, it is another one. That's could be a problem with the glider. Glider is very different. I'm going back and forth the same place. I swim slower than the whales. So there are many challenges in converting this map into population dynamics the way it was done before. But we still have some interesting insights on sperm whale population here. So I have a few examples of how they are distributing towards the shelf, because the glider was going back and forth across the shelf from the coast to the open ocean, or here from the coast to another coast. But you can still see that the whales tend to be more concentrated on some places of this transect, which happen to be the slope here. I also have an interesting observations of the time of the day you hear the whales. So here in the Gulf of Lion, this column here, that is all this part here, and I realized that whales were not heard in the morning. So I don't know why, but it's quite consistent over the two deployments I've made. And this was not expected as a behavior of sperm whales. So that's a new observation that has been made thanks to gliders, and that would not have been possible from visual surveys or even acoustic surveys as a snapshot like I showed during the ACOBAM survey. Gliders also provide oceanographic transects data, so you can collocate your observations to some seawater characteristics, such as here it's mixing. So we are still here in the Gulf of Lion here, where strong mixing events happen in the winter. And you can see how sperm whales may be attracted to mixed water. Going further on this, sperm whales have very cool ways to make noise. So the way they create their clicks, we can hear them. So we hear the click and the reflection on the seabed or the surface. But actually, if you zoom in one click, even more, you see that even the first click of these two here is made of several clicks. And if you look really carefully into how this click is generated, these several pulses, so this IPI is called interpulse interval, is actually reflections within the nose of the whale. And there's a formula that gives you from this interpulse interval the size of the whale. So in addition to seeing or hearing where whales are, I can also have information about what size of whales they are. So that gives you information whether you have males, females, big whales, young whales. So that's a deeper, deeper insight into the population dynamics. Another marine life sound, I can't play that one. It's I think I don't have the proof yet. Fish chorus. So that's the same spectrogram as the one I showed for the wind speed. But now if you zoom on lower frequencies, you see these vertical patterns quite regular. They actually happen every night. So I've zoomed, I have here stacked all the spectrograms here regarding their time of day. So we have midnight in the middle, and from noon to noon, this is the average energy. And you see this increase of energy in this few hundred to 1 kilohertz frequency band. And this is this could be the same fish as the one observed in Diorio et al. Paper in 2018. And the interesting thing of this in the future is that you could use not just sound to detect the fish, but you could use detected fish sound to assess the health of an ecosystem. Just having the glider flying not far from a reef, you can know whether this reef is in a good or bad state and how it evolves within the seasons and the years. Now I'll be quick because I think I'm late already. Anthropophony, so anthropic noise I've recorded with my gliders. There's a seismic survey, I'm not going to play that one. I have a military sonar here. That's it. And maybe that one, that's a ship noise, so you can hear a propeller singing. So that was a random noise measured in the middle of the Mediterranean Sea. That's called singing propeller. It's just a small defect in the propeller of the noise that makes it vibrate and sing like this. And that takes us to my new current project. We have 4 buoys like this deployed in the Saint Laurent Channel, just in front of Rimouski, where I live. So we have antennas of 3 hydrophones in the middle of the shipping lanes. I have the map here. So the ships are going to sail just through this measuring station. And we are working on measuring their acoustic signatures to help build a catalog of acoustic signatures of ship and improve modeling of ship noise pollution. Or I have 4 students working on this project. They will work on comparing and understanding the different sound level acoustic signature measurement methods. One will analyze the correlations between acoustic signatures and ship characteristics, such as speed, age, length, size, type of utilization. Another one will work on multi-source analysis, so going more into details than just a 3rd octave spectra, but actually go thin bands and try and find discriminate the different sources of noise on board one ship. And a 4th student is working on the soundscape analysis of the Saint Laurent measured by this station. So she will focus on the moments where there's no ship through the station to listen to waves, wind, and other anthropogenic noises. Sorry. And that is me. Thank you for listening. I hope I haven't put you too late. I think I'm all right. So just as a summary, these gliders are very effective passive acoustic monitoring platform by the fact that they go into interesting places. They stay at sea for a long time. They are not invasive and are not noisy, which is great for lots of passive acoustic applications. Thank you.
Super. Thank you very much, Pierre. So I can see that we have a comment. Fantastic presentation. Thank you. Yeah, so if you would like to ask a question, then please tap it into the Q&A. But we will focus, we'll round up all the questions at the end after Ahsan has spoken, and we'll do all the questions together. Okay, well, thank you, Pierre. Now, if you're ready, Ahsan, we'll move on straight over to you. Do remember to unmute you're there.
Thank you, Ben. Thank you very much.
Thank you.
Let me just share the screen. Just confirming, you can see the screen? Thank you. Yes, hello everybody. Today I will be presenting a talk on underwater signal processing using arrays on FPGA platform. I'm currently project engineer underwater acoustic design, and my designation is KTP associate. I'll come back to it in a bit. So So today I'll be talking about initially I will be talking about knowledge transfer partnerships. Then I'll discuss about Seish Limited as a business. Then in that more technical bit, I will go into underwater signal processing, how we use arrays, what can we use with, like how can we use arrays to our advantage. Then for the implementation, I'll talk briefly about FPGAs in the end, just to touch the topic a bit, how we can implement things with FPGA. So yes, I'm gonna start presentation now. So yes, the first thing is basically knowledge transfer partnerships. So this is a very interesting concept here in UK. Basically, as a company, as a business, if you have an idea and you want some product development or you want to enhance your business, then you can use the expertise in the academic domain as well. So basically, you can come together with a university as an academic partner, and together you basically hire a person who does the research and development on a specific idea or project. So me as a person, I'm basically a KTP associate, which is a knowledge transfer partnership associate. So it's basically a three-dimensional, in a way, collaboration where we can benefit from the academic side as well as the business side, and work towards like a successful launch of a product. So that's what a KTP is. And it's a very interesting project. It's happening in UK, and there are so many projects currently going on. So I'm one of those KTP associates working on a project, just a bit of KTPs. And basically Innovate UK provides the funding for that. And some of the funding comes from the companies. So moving on. So I'm working basically with the University of Bath and Seish on a collaboration project. Seish, I'll just introduce a bit. So Seish is a company with a mission to advance technology and provide customer-focused services to promote and protect environment. And this is one of the things when I was applying for a job, and it was really I really love the mission statement of Seish, the way they are oriented towards the environmental centric message. What they do basically, they specialize in the design, development, and manufacture of underwater measurement and acoustic systems. So I've included a few of the products that Seish provides. Basically, we provide passive acoustic monitoring system. So you can see here, monitoring system here, along with the array that is used to capture the data. And then we have got the system to basically show the data. We have got different software like PAMGuard, and we can use them to basically do the analysis of the data. One of the key products of Seish is digital thin line array. So it's DTLA basically. So we are using this array for a lot of work at the moment. A lot of R&D is going on, and basically one of the things that we can use these arrays for is potentially beamforming, which is a very key characteristics of arrays, which I'll touch on in a bit. Dual camera system. So basically, dual camera system is a product of Seish, which is basically aiding in marine mammal observation. So it is a very useful product. It's a very recent product as well. It's good, and it's going well in market as well. So it's one of those interesting applications. And also we've got modular buoy systems. So basically these are deployed in different parts of the ocean, and then they have got these detachable arrays with them, which can record data, and that can be analyzed later on. So this was the product side of things. Seish also provides different services, and there are 3 M's, basically modeling, measurement, and mitigation. So Seish provides acoustic propagation modeling. So they basically provide services if you want to see how the source is going to propagate in under the sea, under a different kind of bathymetry in different terrain conditions and different. So basically they can provide those modeling services so you can better understand how the source is going to travel underwater. Also, a very important thing is the measurement of underwater noise. So noise measurement is currently a very important topic because of regulations in the underwater environment and because of the man-made influence. So a lot of anthropogenic influence is there. So Seish is providing the services to measure the ambient noise and the noise levels, which can help in basically, which can help the businesses and the companies to gauge how much noise is being injected into the ocean. So that's quite a key service they're providing in that sense. Third is basically effective noise mitigation through passive acoustic monitoring. So acoustic monitoring, so it helps you to tell, for example, because in the ocean environment we don't see what is under the sea, what marine mammals are there. So one of the best ways, or one of the very good ways to find out is through passive acoustic monitoring, where you can sense if there is a presence of a marine mammal nearby through the sound from the hydrophone arrays, and then you can detect a particular species as well based on the software you have got. So that can help tell the business if there is a marine mammal in the surrounding, and they can plan accordingly if they need to continue with the mission that they are on, or they should stop for a while. This is about the business services. So moving on to the environmental aspect. So two very key aspects of Seish is basically they provide the passive acoustic monitoring operators and marine mammal observers. So these are two very key aspects of Seish that basically with these two, we are able to better address the environmental aspect, and we can inform other businesses of what's going on and how much like influence the business, like how much man-made influence is there, and how we can protect the marine mammals around and generate the wildlife around the businesses. I've included like a citation order here as well. So it just shows you what different kind of marine mammals you can encounter in the sea, all the way to blue whale, like the biggest animal in the world. So one very important thing I wanted to highlight about Seish is the training aspect. So Seish has got a dedicated team for training. They provide year-round program on different topics, different courses. These are basically JNCC certified courses as well. If you want like marine acoustics and signal processing knowledge, then they have a dedicated course for that. They also provide the PAM level 1, level 2 courses, marine mammal observer courses, underwater acoustic sonar systems, and underwater acoustics in the marine environment. So if you are interested in any of the trainings, they have a dedicated schedule every year. You can follow the website details there, and you can book them. I have personally taken trainings, and it has been very useful for me in my personal growth as well about passive acoustic monitoring in general and marine mammal observation. So moving on to that, this is just to show what we do at Seish, one of the very attractive things. So Pierre has already showed some of the key sounds of sperm whale. So I'm just going to show humpback whale here. So hopefully you will be able to listen to that. This is the sound of humpback whale. You can see the mold. So this is what we capture on the projects, different projects, time to time, different recordings. So I just wanted to share with you. Humpback whales are very famous for their songs, and they are like very famous for that. Sperm whales are basically the biggest tooth whales, and they have these clicks. Basically, they hunt using their clicks, echolocation clicks. And this is one just to show you how they can hunt using these clicks. They've got a pattern, proper pattern for that. So I'll just play that for you. And yes, so this was about Seish. Now I'm going to move on to the topic. Yes, coming towards the underwater signal processing and array topic. One of the questions that we can ask ourselves is, why do we need an array? Why do we need an array, and why a single sensor might not be sufficient? So there are different reasons for that as to why we would prefer an array of sensors rather than a single sensor. As you can see here, this is like a one electrode condenser microphone compared to a microphone array, basically. So coming towards the advantages of arrays. So if you got a single sensor, then there's a problem that, for example, if a sensor fails there's a performance failure, so you need some redundancy, and array provides a redundancy in the form of multiple sensors, which can keep operating. Even if one of the sensors stops operating, you can still have more sensors, which will keep performing. Another very important thing about arrays is basically that you can use those arrays, multiple sensors, to increase the signal to noise ratio, because what happens generally with arrays is as all the sensors are receiving signals separately, so you can combine those signals, which results in cancelling of the noise, basically, or basically averaging out of noise, which results in the addition of coherent signals and averaging out of noise, resulting in SNR improvement. So basically, you can get some dBs of improvement in your SNR, which is a very useful characteristic of arrays. It's called array gain. Another very important characteristic of sensor arrays is beamforming, which I will talk about primarily today in my talk. So beamforming is basically a key property, which means directivity. So it's just like when you use filters to filter out the unnecessary frequencies and keep the important frequencies of interest. So beamforming using arrays, sensor arrays are basically like a special filter. So they can basically help us in filtering signals from different sides, so depending on the directivity. And I will talk about that. So you can reject some interferences from unwanted directions, and you can keep the signals that you want. Also, because you've got multiple sensors in an array, so they receive signals at different direction at different times. So there's a time delay. So using those time delays, you can find out the direction of the signal, where it's coming from. So one of the key applications of arrays is you can localize signals as well. Yes, moving on to some of the things here. So let me just, yeah. So the main thing is most type of antennas transmit about the same amount of power in all directions, and we can ask where do we need directivity? So some of the examples where we do need directivity might be a radar communication or anti-submarine warfare. There are a lot of applications. So normally, if you see a particular sound source or an antenna, it might have a pattern of power or radiation like this. For example, as you can see, this water droplet, it's dropping in, and there's equal amount of energy radiated in all the directions. So it can give you an aspect of like omnidirectional kind of antennas. But if we want the directivity, then this might not be the solution. What can we do? Basically, we would want an antenna with a narrow beam in a particular direction. For example, as you can see, for example, we might be focusing on a particular direction like this. So we need a narrow beam. And to do that, we'll see how we can achieve that. So moving on to this. Yeah. So how can we achieve the directivity? So the bigger an antenna in size, basically the more directivity is. For example, you can see a satellite dish here. So if you can make an antenna big, it will be more directive. It will focus much more better than an omnidirectional antenna. But there's a problem. So the bigger your antenna is, the problem is the bigger size. If you want to change the direction, then it's very difficult to do that as well. They're massive, bulky objects, and it's not easy to change the directions. So there needs to be done something about it. How we can achieve directivity without having those bulky big dishes. We can do that, and the answer is in the form of phased array antennas. So phased array antennas are basically a group of antennas, as you can see an example here from RF Microtech. So they've got a lot of sensors here, a lot of small antennas here, which are basically comprising of phased array. So how do they work basically? So rather than having a big dish, what you can do is you can have a lot of small small antennas, basically at a fraction of the size, basically, and they can all work together. And how they work together. So I got this very useful resource from Mark Hickel, and he explained this very beautifully as well in his one of his videos. So basically, you can just use multiple sensors, and if you see here, so basically, when you have got like multiple sensors here, so they can when the same source is propagating out from those sensors, what happens is in the air they create a pattern. It's like a constructive and a destructive interference pattern, and as a result of that, the resulting beam is only focused in one particular direction. So as a result of this, you achieve a directivity. So here you can see as a resultant, you are achieving directivity. And you can see this here in this animation as well, where you will see like 2 water droplets coming from like, it's like modeling 2 different sensors basically. So if you have a look at this one.
Interference, forming a main beam perpendicular to the drops and canceling each other out in these other directions. We also see these other beams to the side. These are called side lobes, and although they aren't...
So basically what you saw in this one is basically both of these droplets are coming from 2 different sensors, and they are happening at the same time. So they don't have any delays. So what happens is they are creating like this main beam which is perpendicular. So you are achieving kind of directivity because of this concept. So that is very useful indeed.
Interference.
So moving on from that, a very interesting question will be, what do we gain from replacing a big dish with a phased array? The answer to that is beam forming. So the beam forming is basically the ability to change beam direction electronically without mechanically steering of antenna. So you might have seen a lot of radars basically which are moving around. So they're mechanically steering all the time. So rather than that, beam forming basically allows us to electronically steer the antennas, and using what? Using some different time delays, using phases. So basically we provide different time delays to the sensors, and as a result of that, you get a beam that is changing in direction, and you can basically scan throughout, as you can see here as well. Let me just show this one here. So if you can change the delays, relative delays, so you get something like this, which is like a scanning beam basically, and it helps you to electronically scan, and you can basically achieve your directivity in that sense. And this is just shown here.
They don't hit the water at exactly the same time, and that changes the direction of that main beam. We can see here that as we change the timing, we can actually steer that beam back and forth.
So
they don't hit the water.
So that was just about some introduction to the beam forming, and this is something really useful about beam forming as well. Beam forming is, so if you see here on this side, on the left side, you can see here, I've got different sensors here, and we are basically providing different phases to them, to the different sensors. And if you don't give any delays to them, it will be focused perpendicular. But if you want to change the direction, you can give different delays relatively, and as a result of that, the beam will be focusing in a different direction. So it's all about feeding those different delays to the different sensors, and overall you can change the look direction of the array as a whole. Here you can see the array in general basically. So these are the different sensors here, and you've got a broadside array here. So broadside is basically the perpendicular direction to the array, and we can measure different angles with respect to that. So you can see this very nice animation of how you can change the beam direction by just altering those phase delays. And so this is further to beam forming. So basically, if you see here, we've got 3 different sensors here. And for example, if we imagine that a signal is coming from this side, it's minus 45 degrees with respect to the array. So it will reach this sensor first, and it will reach this sensor later on. And the array output will be like this. So it will be like, it will have, so all the signals will be arriving at different times. So overall, you won't be getting a maximum signal. But if the signals are coming straight from the perpendicular of the array, all of them will come at the same time, and they will add up to form a bigger signal basically. Similarly, if you are getting a signal from this side, it will reach this sensor first and this sensor later on, and then you will again not have a high correlation. But you can do something with that. What you can do with that is you can so if, for example, if we have got a target wavefront, for example, if this is our desired signal, and then there's noise coming from other directions, so we can allow our beamformer to basically align the signals in a way so it can maximize the signal from a particular direction. So what it does is it's basically adds proper delays so that the signals are aligned in time, and when they're added together, they basically maximize the signal, and as a result of that, you get a big signal from the desired direction, and you can get the noise becomes averaged out in that sense, and you don't get signals from unwanted directions. So this is one of the key things about beamforming and how we can achieve array gain using the beamforming technique. How you can achieve increase the directivity of the arrays it can be achieved by increasing array aperture, and you can increase the array aperture in two ways. Either you can increase the number of antennas, or you can increase the inter-element spacing or spacing between the sensors. So this is one of the examples of the world famous ALMA telescope in Chile. You can see here, basically array aperture basically means the maximum distance between the sensors or the arrays or the dishes basically. So although they are big dishes, but they combine together in the form of a big array to form like a very big array, which is called ALMA. And it has helped solve a lot of mysteries about the universe as well. So this is all about like how you can combine multiple sensors, dishes to form a big, huge array. This is an example of how we can increase the directivity by increasing the number of antennas. So I have shown here an array with 8 elements and another array with 24 elements. And I've shown the beam pattern of those arrays. So the array basically has an inter-element spacing of 1 meter and a frequency of 750 hertz. So what I did is I increased the aperture by adding more elements to it. So you can see here with 8 elements, I have a very wide lobe in the direction that I'm looking. So it's not very directive. It's got a very wide main lobe. But if I increase the sensors more, so rather than 8 elements, I go to 24 elements and keeping the same spacing, I can achieve increased directivity. So you can see the beam has become very narrow. So you can achieve directivity by increasing the number of antennas. So that's one of the ways you can do it. Another way to do it is by increasing the inter-element spacing. So initially it was 1 meter of spacing, but what I did is I tried to increase the array aperture by increasing the spacing from 1 meter to 2 meters. So what happened as a result of that, I kept the elements same, both with 16 elements, but I just increased the spacing in the second figure. But what happened as a result of that is this beam becomes a bit narrow, but we also see another lobe being introduced. This is because we have increased the spacing beyond what is basically required. So this is a disadvantage, and it sets the limit of how much you can increase your inter-element spacing in order to achieve the directivity. Because what that means is now you are directive in this side as well as this side, which might not be the desired effect. So this was about it. So all of these concepts apply to the underwater environment as well. So basically, rather than microphones, we have got the hydrophones, and we can do the underwater acoustic beam forming using different platforms. So here I have an unmanned underwater vehicle, which is called a UUV, and we can basically use it as a platform, and we can attach an array with that. So it's going to tow an array, and the array basically will be comprised of multiple hydrophones, which will be able to do the beam forming that we want using multiple sensors. And then we have a processor in there, which can do the beam forming using different delays. And as a result, when we use this equipment underwater, we can look in different directions. As a result of that, we can find out if there's a presence of a source in a specific direction or not. So this is one of the very big applications of underwater acoustic beamforming. Last, I will just explain a bit about the FPGA, how we can use the FPGAs for signal processing. So FPGAs basically are field programmable gate arrays, and they are semiconductor devices that are based around a matrix of configurable logic blocks, CLBs, connected via programmable interconnects. So what is that thing in FPGAs that is very attractive? So the thing about FPGAs is you can program them anytime, you can reprogram them, and they are comprised of a number of logic gates. At the moment, I think the devices we are getting they are running into like hundreds of thousands of logic gates, and you can basically implement any kind of design that you want on that hardware, and it will basically be synthesized using the technology. Okay, so you can implement whatever functionality you want on that hardware. And why FPGAs are also attractive is because they are very parallel kind of devices. So they allow you to achieve a lot of parallel functionality. So you can, for example, if you want to implement some kind of filtering or beam forming with delays, a lot of things that you want to keep doing and doing and doing, you can do a lot of parallel things in FPGA because it allows you to do a lot of parallel implementation. So a lot of things can happen at the same time compared to like a sequential processor, like your computer, like normal computer, which does things in a sequential way. So FPGAs can do a lot of things in a parallel way at the same time. That's the beauty of FPGA. So I'm working on FPGA design at the moment as well, and it has this is one of the very beautiful things about that you can implement things in parallel, but you just have to understand the architecture a bit more. So you can use MATLAB to code your own design if you don't know the language of VHDL or Verilog, which basically is used to code for FPGAs. But you can use like converters from MATLAB to VHDL or Verilog, which can convert your code in a language that can be implemented on the design. Or you can basically write your design in C, and then you can convert that into the VHDL using tools. There are a lot of tools from Xilinx that you can use. There's a tool from Xilinx tool called Vivado, which you can use to design, to create your designs. Basically, you can write codes in there. You can create block diagrams in there, and you can implement your designs. So it's a really, really useful functionality for implementing your signal processing designs. Yeah, thank you very much for that. I think I might have taken a bit more time than I was given. That's pretty much it for me, and thank you for listening to me. Any questions, please? Thank you.
Great, thank you very much, Ahsan. So yeah, opening up to questions now. Either you can type your questions into the Q&A at the bottom, or if you want to speak your question, then you can raise your hand, and I believe I have the power to ask you to unmute. So yes, but I will kick off. So Pierre, I was wondering, using your gliders, at the beginning you talked about the wind speed. How did you validate your measurements of wind speed from the glider against well, something else?
Against reality. There are on the way of the gliders, each of I had 4 deployments on 2 different lines, and all of them had a weather station mode in the middle. So there are meteorological buoys in these parts of the Mediterranean Sea, and we specifically tried to get the glider as close to them as possible each time they were sailing past. So if you look at the one between France and Corsica, we'd go across maybe in 2 weeks, and that means every 2 weeks we are for 1 day not far from the weather station, and then we can cross compare there. So that's how I've done the calibration.
Great. Okay, and well, I guess on the same note, how does a glider know where it is? What navigation capability does it have?
It has something very fancy called GPS when it's at the surface. So there's an antenna each time the glider surfaces to actually know where it is. Like you when you're swimming, you can sometimes pop your head out and look at where you are. And then there's dead reckoning systems when the glider is underwater. So we have a flight model. So the glider knows roughly how much forward distance is made for each meter vertical, plus accelerometers, when it's turning. But yeah, it's navigating with its eyes closed when it's under the water, trying to guesstimate where it is. And then once it's out of the water again, another GPS fix to know how much the error was. And it's actually not an error, it's just a way to estimate currents in along this dive, because gliders can't feel the currents because they would be moving with the water mass. And that's the only part that the dead reckoning cannot model. So we use this error to estimate average currents along the path of the glider.
So when you pop up, you're 200 meters away from where you think you ought to have been, then that gives you an estimate of.
Yeah, that's it. Yes.
I see.
Yeah, they're quite good actually. Much better than you think at dead reckoning where they are.
Yeah. Yeah, I was imagining that they would have some sort of inertial system.
There's accelerometers. You don't want to have anything too power hungry on board or heavy. So no, nothing really fancy, but the flight models are quite good.
Yeah, of course. So I think all of your measurements that you showed were a single hydrophone.
Yep.
do you see any advantages to doing some array processing? I understand that every piece of kit you put on the glider means it's in action for less long.
Yeah, now that I'm working with big moorings and 12 hydrophones and expensive and heavy hydrophones, I can really see or hear the difference. There's a real constraint of weight and power on a glider. So do I want to have 2 hydrophones? Yes. Do I want to shorten my mission by half? No. So I think the way forward with gliders is to go lightweight, 1 hydrophone, maybe 2 hydrophones. There are systems now that can carry up to 4 hydrophones, commercial ones. I know people who have 10 hydrophones on their gliders, but the missions are different. And as long as I'm working with oceanographers who want their gliders to go far and for a long time, the real challenge is to do decent acoustics with a small scale hydrophone.
Yeah, I understand. So Ahsan, you mentioned a bunch of different methods to implement code on FPGAs. What are you using at the moment, and would you recommend it?
So yeah, so currently, so when I started working on the project, one of the things that I faced was I'd worked in MATLAB a lot before personally. So when I went into that like mode of like working with MATLAB and then trying to convert that code into the VSDL environment or a Verilog environment, I had to depend entirely on the code conversion tools, like for example hdlCoder. So MATLAB has got this tool called hdlCoder, which can do the job for you. So you can write whatever code you want at a very high level of functionality. So you don't want to understand what is the lower level of hardware that's going to be inferred from that. So you can just model your design, create a design in Simulink, or create a design in the MATLAB environment, the script environment. Check its functionality is okay. You can check it with like different tools. Once you're happy with the performance of the design that you have created, then you can use the tool to convert that into the code that you want. For example, the VSDL code or the language of your choice. So they have got these tools like hdlCoder. You can run the process properly. It will tell you about different like errors if you have got in your design. You can test the real-time environment and the real-time testing of your code on the FPGA as well. So basically the hdlCoder tool allows you to test your design all the way with your converted code in VSDL or Verilog running on a FPGA in live. So it can test everything. One of the challenges might be that once you've got that code and you start implementing it on the FPGA, you might try to debug it, maybe try to see if everything is okay, if the signals are right, if the result is okay, and you might come up with some problem in the design. Then you might have to go and find out where the problem is. So what I felt personally for me is, if you don't know the language like VSDL or Verilog, it can be a problem if you have to debug the code that was basically produced by the coder, by the tool, and then you would be in a problem how to understand that. So it can be very good from the functionality that you don't have to know the language, the lower level language. You just create your design and that will be it, and the tools will make everything okay for you. But in case you have to debug it, if there are problems, because the tools can only do the job at a certain level of performance. They might not be able to do it 100%. And sometimes writing your own code can be more efficient than depending on a conversion tool that will convert it for you. So that is one thing that I felt that is really important. Now I had to debug my own code. So now I'm learning VSDL on my own side as well, because I felt that it's important. If I want to debug, I need to understand the language as well. So I would say it's good to know MATLAB or C language. But if you have to understand and debug the design, you might have to come up with some understanding of Verilog or VSDL, because these two languages are going to be needed for FPGA implementation.
Right. Okay. Super. And is there a big sort of barrier to entry to Verilog or VHDL?
Come again, Ben?
What's the learning curve like for VHDL or Verilog?
just like any other programming language, not difficult at all. You just need a learning mindset, and it's absolutely fine. I myself got some training from Xilinx, and they're really useful trainings as well. And I'm learning VHDL these days as well. So there are really nice tools available. YouTube videos are there. There's a lot of useful stuff around there, so you can learn it easily. It's just you have to practice more. You have to spend some time on it. But I think it's as a digital designer, if you want to have a career path, you need to know the language.
Right.
But as the researchers, most people like me, I prefer to stay on the MATLAB level. But now I see myself as I have to go at that level as well, because you need that level of a skill to better debug your designs.
Yeah. Okay. And just before we finish, I think we've just gone over the hour. Pierre, I wanted to ask you about. You mentioned the resonating of the whale's click inside its mouth, telling us the dimensions of the whale. I wondered if there's any extra information in that interesting interval or around that to tell you not only this is a whale of this size, but this is a specific whale, and maybe that could help you with the with knowing whether two whales that you spot are the same whale or a different whale.
Yeah, that one is a bit of a fun fact to me. It's actually much more complicated. That's why I showed these reflections are just the fact that the way it's generated in the head. So you have reflections within the head before being projected forward. This is highly directional. So if you hear this from the front or from the side, you will have a different pulse interval, but obviously it's the same whale. So I know people are able to find the size of the whale. It's more complicated than the equation I've shown. That is, I think, from '87. There are papers out there that are much more accurate or robust. Now, as far as I know, no, you cannot ID George the sperm whale just by its clicks like this. But when you are within a group of whales, you can probably track the 15-meter whale and know where it is 5 minutes after. So if you come back a month after, you're down to, I think the only way is photo ID at the moment for whales. So you'd have a nice picture of their tail, or like they'd have marks, imperfections on them that you can recognize years after. But with the acoustics, I think you may be able to do something within a few minutes or hours, but it's not a proper ID.
Understood. Okay, well, thank you again very much for presenting.
For having us.
Thank you.
And yes, just for the remaining attendees, our next webinar will be next month, and our theme will be transducers, and so we have Hannah Rose, who is a part-time PhD student, also at Thales, and we have Zoe Rymansaib from the University of Bath. Okay, well, thank you very much again, Ahsan and Pierre. And yeah, look forward to seeing people next time. Thank you and goodbye.
Thank you very much, Benjamin. Thank you, everyone. Thank you.